The Constitution of India, Preamble. We, the people of India, having solemnly resolved to constitute India into a sovereign, socialist, secular, democratic republic and to secure to all its citizens justice, social, economic and political, liberty of thought, expression, belief, faith and worship, equality of status and of opportunity, and to promote among them all fraternity, assuring the dignity of the individual and the unity and integrity of the nation. In our Constituent Assembly, this 26th day of November 1949, do hereby adopt, enact and give to ourselves this Constitution.
Happy morning, students. I hope you all are good and all are getting up early now, because I could see the messages from you all and I am so happy. We have started our exams as well, and don't worry about the marks that you are getting in the exam. It is just an exposure that you are getting in your question paper, like the time management or what type of questions you need to face. All those things only we are getting in the question paper. So, and I know you all are doing good, because I could speak to some of the children right after the exam. I could see the happiness in your face, because many children have told it's good that we are writing this exam. So, always take it in a good sense, start preparing, no need to strain yourself, enjoy your work and do it. So, definitely it is going to earn you good results. So, now we have started with the topic states of matter, and we have almost seen 4 gas laws. Now, when we were seeing about ideal gas equation, I told you ideal gas is a gas which behaves ideally, which means that obeys all the gas laws like Boyle's law, Charles' law, Avogadro law and other laws. So, from the ideal gas equations PV equal to nRT, we came to know that PV, P1 V1 by T1 equal to P2 V2 by T2, which is called as a combined gas law, which is connecting all the Boyle's, Charles and Avogadro law together, and this we call it as combined gas law or equation of state. From this we are going to derive a formula to calculate the density of a substance. How shall we do it? Or with density, how can we find out the molar mass, that is the molecular mass? Now, that is when you take the ideal gas equations, we know PV equal to nRT, N by V equal to P by RT. Now, but we know number of moles can be calculated by given mass by molecular mass. So, when I substitute this in the equation, M by V into M is equal to P by RT. So, when I know mass by volume equal to density, which we have already learned, D by molar mass equal to P by RT. Rearranging the equation, we will get molar mass will be calculated by dRT by P, which is the formula that you will be getting in your exams for the problem's sake. From this we came to know that using the ideal gas equation, we can also derive the formula to calculate the molecular mass of a substance. So, here 5 parameters are there, where R is a universal gas constant. Knowing any 4 parameters, we can calculate the unknown parameter. Now, once we know this, we should always be worried about the pressure that is being exerted by the substance in a container, whether it is inside or whether it is outside. So, that is why a new law, that is Dalton's law, which we have already learned, Dalton's law of partial pressure, that shows that there will be a container and there will be molecules of different types, like molecule A, molecule B, molecule C, different types of molecules. Each molecule or each substance will be exerting a separate individual pressure. Say P1 is from the first molecule, P2 is pressure exerted by the second molecule, P3 is the pressure exerted by the third molecule. So, what happens in that case, the total pressure exerted in the container will be equal to sum of the partial pressures of the individual substances. So, calculating the sum of the partial pressures of all the molecules, we will be able to find out the total pressure of the container exerted by all the molecules. Now, there is something called as aqueous tension. What is aqueous? We know aqueous medium means something which is having water content, that is moisture. The pressure exerted by saturated water, we call it as an aqueous tension. Now why this comes is because any substance will have some of the water molecules present in it, that is hydrated. So when I want to calculate the pressure of the dry gas, because we are studying about the gaseous state of a molecule. So if I need to calculate the pressure of the dry gas, how can I find out? It is the total pressure minus the aqueous tension. So when this aqueous tension and total pressure has been removed, when water pressure is removed from the substance pressure, we get the pressure of the dry gas, because when water removed, the substance becomes dry. So that is how we calculate the pressure of the dry gas. Now let us see how this has an application in calculating the pressure, volume and temperature of a gas using the Dalton's law. Now let us see how can we derive the partial pressure, because we have learned in Dalton's law that the total pressure of the gas will be equal to sum of the partial pressure of the individual components. So here if I want to find out the partial pressure in terms of mole fraction, how should I do it? Now if T is the temperature of any gas and V is its volume, P1, P2, P3 is the partial pressures of the components 1, 2, 3. Now let us assume this. So how can I calculate P1? P1 will be, we know PV equal to nRT, so P is equal to nRT by V using the ideal gas equation. So for the first component P1, it will be N1 RT by V, and for second component P2, it will be N2 RT by V. For third component P3, it is N3 RT by V. R, T and V are remaining constant. Only N1, that is the number of molecules in the first component, second component and third component varies. So N1, N2, N3 are the number of moles of each component. And we know in Dalton's law, the total pressure equal to sum of the partial pressures. So in place of P1, substitute what is P1. In place of P2, substitute P2 value, and in place of P3, substitute what is P3. Now, we know RT by V is common in all the three equations. So what we'll do? We'll take RT by V as common and we'll take N1 plus N2 plus N3 as a one substance. So what happens here? N1 plus N2 plus N3 into RT by V. Now on dividing, what are we dividing? We are dividing this P1. This P1 I am going to divide by P total, that is the total pressure. So what will I get? P1 by P total will be equal to, this is N1, N1 by N1 plus N2 plus N3 into, this is RT by V divided by RT by V. So how do we get here? RTV, RTV. When you divide the same components, you get like that only. So these two, they get cancel each other, RT by V get cancelled, and what do we get here? P1 by P total equal to N1 by N1 plus N2 plus N3. Now this N1 plus N2 plus N3, I can take it as N. Total I can consider it as N, that is the number of moles, which is equal to sum of the number of moles of each component. So N1 by N, I again put another variable which is x1, which is called as a mole fraction. So what is x1? The number of component of 1 divided by the total number of component. That is the number of moles of components of A divided by the total number of components. So that is N1 by N, which is equal to x1, that is the mole fraction. So from this I know P1 by P total equal to x1. So what will be P1? P1 equal to x1 into P total. So P2 will be equal to x2 into P total. P3 will be equal to x3 into P total. So in general I can write for the ith component of any gas, Pi is equal to xi into P total. So this I can be the first component, second component, or any component that is present in the gas. So that will be equal to the product of mole fraction into the total pressure exerted by the gas. So I hope this you understood, children. Now the next important topic which we will be learning now is the kinetic theory of gases. Let's learn the kinetic theory of gases. What is kinetic? We know static means rest, kinetic means something in motion. So if we are going to see the kinetic theory of gases, as I always say, gases have random motion. They do not stay at a particular place, right, just like solids or liquids. Gases, they are in continuous motion. So when they are moving continuously, they collide with each other and also with the walls of the container, which we have learned in 10th standard that they are perfectly elastic. So when they are moving, their speed and energy are not constant because they not move in the same constant speed. They move with different various speed. So if I want to calculate the speed of the molecule, I will not be able to calculate the speed. Rather, how will I calculate is through the average. How do I find the average? If U1, U2, U3 are the speed of individual molecules, the U average, the speed average will be the speed of all the molecules, sum of the speed of all the molecules divided by the total number of molecules. That's how I get my average speed. But when this was studied by two scientists, Maxwell and Boltzmann, they said that the speed also depends on two important factors. One is the temperature, the other one is the molecular mass. And as we have already learned, temperature is a very important factor because when we increase the temperature, the molecules tends to move, they tend to collide with more force, that is with more speed. So what is concluded in this is when we plot a graph at various temperature, at lower temperature the speed was not to the maximum, but when you increase the temperature there were maximum number of molecules reaching the most probable speed. So the most probable speed is defined as UMP, where the speed exerted by the maximum number of molecules. And if you see, the maximum speed will be by the not very high or not very low, but the most probable speed will be the more number of molecules exhibiting the same speed. When we increase the temperature, the maximum probable speed, that is the most probable speed, also increases, because children, we know when temperature increases, kinetic energy increases. The molecules tend to gain more energy, they tend to move or collide with each other with great force. But when you increase the molecular mass, you can see that the speed actually decreases, because as we know, when I throw a small ball or when I throw a heavier ball which can go faster, right, that's because the molecular mass plays a very important role, that they will not be able to run at a faster rate or collide with a faster motion. Rather, the molecules with lighter, that is lighter gaseous molecules, tend to have more probable speed compared to the heavier molecules. So overall kinetic energy will be defined as half mu square. So u square can also be given as u1 square plus u2 square into u1 square divided by n, which is the total number of molecules. So that is how the kinetic theory was distributed. It was just analyzed by the scientists for various issues. And now we will be also learning about the kinetic molecular theory in detail to know about the various application of gases in different. Seeing about the kinetic theory of gases, now you will see a video where you have the postulates of kinetic theory. And there are some gases which deviate from their ideal behavior, and those gases are called as real gases. Now if you see, why do they deviate from their ideal behavior? If a graph is plotted between the pressure volume and pressure here, you can see this is an ideal gas where you have a straight line. But when I take four gases like hydrogen, helium, carbon monoxide and carbon dioxide, for hydrogen and helium, the gases are actually a straight line, that is they increase with increase in the temperature. But what happens with carbon monoxide and carbon dioxide, they first show a negative deviation, they go down away from the ideal gas, and later with increase slowly they keep on showing a positive deviation. But when you plot a graph only between pressure and volume, this is the real gas and the ideal gas behavior where there is a point of coincidence. Real gases are those where they do not obey the gas laws, especially when you see the Boyle's law, they go against the Boyle's law. Now why do gases deviate from the ideal behavior? What are the reasons for their deviation from the ideal behavior? What are the conditions that cause the deviation? Why it makes the ideal gas behave like a real gas? It does not obey the gas law. There are so many reasons and so many investigations done. There were two assumptions made. The first one was there was no force of attraction between the molecules of the gases. The second one, the volume of the molecules of gas is negligible as compared to the total volume of the gas or total space occupied by the gas. If I say the first assumption is correct, then I should say that there will be no collision against the walls of the container or between the molecules. But definitely there is a long force of attraction. That's why we say the molecules, they collide each other. But what happens if the pressure is more? If the pressure is more, they tend to attract towards each other, hit each other, but not with the walls of the container. That becomes less. If I say the second assumption is correct, again when the volume is negligible, definitely there is no coincidence happening. They should not collide with each other. But now we came to a conclusion that when I say the pressure of an ideal gas is equal to pressure of the real gas plus AN square by V square, where N is the number of molecules and V is the volume, A is the constant. So this is the correction term where the real gas shows this much variation, so that when that variation is taken into consideration, they behave as an ideal gas. So when I say pressure of an ideal gas, it will be sum of the pressure of real gas plus the deviated term. This much is the deviation that is happening in an ideal gas. So that is how the assumptions are made for a real gas which deviate from the ideal behavior. Let us now learn about we were just seeing about the gases, that is with occupying a small volume where it is negligible with two assumptions. But the same thing is here only when the repulsive forces are in contact. When we say there are repulsive forces, see there are intramolecular forces which are weak forces, which we call them as van der Waals forces. Now children, assume the attractive forces are those which binds the other molecule towards itself, and there are repulsive forces which also pushes the molecule away from each other. So when there are so many number of molecules and the repulsive forces are acting in all direction, imagine if I am going to repel you, there might be other molecules where you may get attracted. So my repulsion can make you in contact with the other molecules. These repulsive forces are short range interactions which make the molecules behave as a very small, such that the volume occupied, actually instead of moving in a big volume, they move in a small volume of V minus NB. Because here we are talking about the gases which do not obey the gas laws, that is which deviate from the ideal behavior. In such cases, when I say PV is equal to nRT, in place of the pressure of real gas, let me just substitute P plus AN square by V, which is the pressure of a real gas, and also volume of real gas, where V minus NB is equal to nRT, where A and B are the van der Waals constant, and the whole equation we call it as van der Waals equation. So these are the negligible change in the volume and the pressure that has been created among the gas molecules. Now what happens to these forces? These forces are actually significant. I mean, you can easily find out how the forces are existing between the molecules. Now at low temperature, what happens? You can easily see how the forces actually react with each other. And when the pressure becomes absolutely zero, that is at vacuum, when there is no pressure, the real gases starts behaving ideally. So real gases, they actually deviate because of intramolecular forces, and we said that there is a change in volume, but when the pressure becomes absolute zero, these real gases, they behave ideally. So there is a compressibility factor which helps us to find out the deviation in the behavior. So how much is the deviation in the behavior? Now that factor we call it as a compressibility factor, and that is denoted by the symbol Z. So Z is equal to PV by RT, where we know P is the pressure, V is the volume, R is the universal gas constant, and T is the temperature. Now what happens to this compressibility factor? For any ideal gas which obeys the gas laws and behave ideally, Z is equal to 1, where PV is equal to RT, and N being the number of molecules which we already know. So for any ideal gas, the compressibility factor will be equal to 1. And what happens for real gases, that is which deviate from the ideal behavior, there are two values of Z where it can be greater than 1 and it can be less than 1. So at high pressure conditions, the value of Z is always greater than 1, and for intermediate pressures, the value of Z is always less than 1. Now gases, they behave ideally when the volume of the gas is so large that the volume occupied by the gas molecule is negligible. What does it mean, children? See, I have a container where there are so many number of molecules, gas molecules. The total volume occupied by the gas molecule in the container is so large that the volume occupied by each gas molecule inside the container is negligible, which means it is so small that you cannot take into consideration. So in that cases, every gas starts behaving ideally. So that is the condition where the real gases also start behaving ideally when the pressure becomes absolute 0. Okay. So let us now learn few terms which are the boil point or the boil temperature. As we are learning about Boyle's law, which states that at constant temperature, the pressure of a gas is inversely proportional to its volume, which means as the pressure increases, volume decreases and vice versa. So what happens here is, what is a boil point or a boil temperature? The temperature at which the real gas behaves ideally over an appreciable range of pressure. What does that mean? There are several pressures which keep on changing. So over an appreciable range of pressure, over some pressure points, there are real gases which can behave ideally at a particular temperature. Now at that temperature, we call it as a Boyle's temperature or boil point. Above the boil point, the real gases show positive deviation, which means there is a slight increase in its curve where the compressibility factor Z will be greater than 1. Now what happens when the pressure is low, or when we say it is below the boil point? The value of Z also decreases first with decrease in pressure, and as the pressure keeps on increasing, the compressibility factor also increases. So as we know, Z is equal to PV real by nRT. As PV is equal to nRT with ideal gas equation, let us calculate for the compressibility factor. Now if a gas behaves ideally, let me write volume ideal will be nRT by P, because it obeys the gas law. Now when I substitute the value of nRT by P in this equation, nRT by P, the value of Z becomes V real, that is the volume real by the volume ideal. So it gives the ratio of the actual volume occupied by the molecule of a gas. So this value of Z is the compressibility factor. So that is how the kinetic theory of gases has been explaining us how the real gases behave ideally at certain temperature and pressure conditions, and what are the factors through which the gases start deviating from the ideal behavior. And always remember, an ideal gas is a gas which can behave ideally only because it obeys the ideal gas equation or the laws, that is a gas laws like Boyle's law, Charles' law and Avogadro law. So any gas which deviates from the ideal behavior is just because it does not obey the Boyle's law, or maybe there is a change in the intramolecular forces of attraction. So with this, let us stop the class here, because we will be continuing about a very small topic in the very next class, which is liquefaction of gases. So I will be posting the videos along with this for the better understanding. Still, if you have any doubt, children, kindly get back to me, and make sure that you read the text very carefully and underline the important terms that has been discussed. Okay. Thank you, children. Take care.